Alrighty, in this video, let's talk about some formal charge. Um, the formal charge is something that gets a little bit confused. I don't know. I think maybe a lot of stuff in Gen Chem gets confused, but formal charge isn't so bad. Okay, I hope. Um, so let's just dive in and keep charge of it. Um, Formal charge. We're talking about an electron. This is an electron bookkeeping method. Uh, we're trying to figure out which atoms. This is good for figuring out which atoms in a compound bear the charge. Like if you have a polyatomic ion, we can figure out where the charge is. If you have a variety of Lewis structures that are all reasonable, it'll let you figure out what the best Lewis structure is. Um, and we can calculate the formal charge based on a valid Lewis structure. So as long as you have a valid Lewis structure, we can get the formal charge taken care of. This is how we calculate formal charge. The total number, this is all on an atom. Okay, so your formal charge on the particular atom is how many valence electrons they started with in the Lewis structure. Well, on the periodic table, so group 6 would have 6 valence electrons. You know what I mean? Okay. Then we're going to subtract out any non-bonding electrons, and we're going to subtract out half of the bonding electrons. And all of this is to that particular atom. And I'm going to work some examples so we can see how this goes. Okay. An easy way to do this, especially if we're having a Lewis structure, because you kind of have to have a Lewis structure to get this under control. Your non-bonding electrons, you're counting how many dots are on the atom. Okay. Half of the bonding electrons, you're counting the lines that go to that atom. Okay. Yeah. So yeah, so we're thinking about formal charge is always relative to one specific atom, right? You can do it for all the atoms in a molecule if you want to, but we're thinking about the charge on an atom. It's important to remember this is hypothetical too. It's not necessary. I mean, sometimes it relates to an actual physical charge and sometimes it doesn't, but that's beyond our discussion today. So some things to remember. We're talking about the charge on one atom. The total formal charge in your Lewis structure is going to be equal to the total charge on the formula. Okay, and I'll show you what I mean by that in a bit. Okay, and the atoms that look the same in the Lewis structure are going to have the same formal charge because we're counting dots and we're counting lines. And if it's the same element and the bonds and the dots are the same, then they're going to have the same formal charge. So it lessens the number of things we actually have to count when we're doing the formal charge. Okay, let's do ammonium as an example to warm us up. Okay, we're going to draw a good Lewis structure for ammonium. So nitrogen in the center, 4 hydrogens around the outside. That's 8 valence electrons. We had 8 valence electrons. For completion, I'm going to put the positive charge there. Okay. Now, if we look at this, all of the hydrogens look the same. Every one of these is a hydrogen with a single bond and no dots. Okay, so when we count this up, we can count it up. We can count the hydrogen once instead of counting the hydrogen 4 times and get the same result out. So the way I'm going to think through this is I'm going to make a table, and I do this with all of my formal charge stuff. It's the best way I think to keep things straight. We're going to count things with hydrogen and we're going to count things with nitrogen. So we're going to do that. What we're counting is how many valence electrons we started with, how many non-bonding ones are in the picture, and how many bonding ones or half of the bonding ones are in the picture. So this is our dots and this is our lines. Okay, adding all this up is going to give us the formal charge. Okay, so if we look at those hydrogens, every hydrogen in here is the same, right? Hydrogen starts with 1 valence electron. The hydrogens have no dots and they have 1 line. So we're going to subtract 1 line. So this formal charge is 0. Remember, our formula was saying that valence electrons minus non-bonding minus a half. So everything we're counting here is going to be negative. So as we do this, for the nitrogen in the center, nitrogen starts with 5 valence electrons. There's no dots on this nitrogen. There's 4 lines that go to the nitrogen. So for nitrogen, we're counting all of this. Okay. And there's 4 lines there. So 5 minus 4 is a positive 1. So what this tells us is, right, our good double check is, right, 4 times 0, because we have 4 hydrogens, is going to be 0, plus 1 is plus 1. So our Lewis structure has a charge of plus 1. So this all works out. The total formal charge is that the formal charge, what the charge on the formula is. Okay, makes sense. Let's take a look at another example. Let's determine the best Lewis structure for cyanate. And instead of me drawing all this out, I'll have nice pictures for you. Chances are, if you're given this compound, this is the first Lewis structure you're going to draw because it looks nice. It's symmetrical. It's kind of what our brains like to do. Okay, but there's other options for this. You have 2 other structures that look like this. Okay, where there's a triple bond and a single bond, either this way or that way, instead of 2 doubles. Okay, these are all valid Lewis structures. Your whole thing is you have to have a valid Lewis structure. Now, because the bonding in these is different, there's one of these that's going to be better probably than the other 2. And so our goal is to determine the best Lewis structure, and we can do that by employing formal charge. Okay, so let's make our table: valence electrons, non-bonding electrons, and bonding electrons. And we're going to use that to calculate formal charge. And I've got this set up so that they line up under the atoms. This is a great way to do it. Here we're going to have to count all the atoms in here because we don't have things that look the same. Okay, so let's do this. Let's say, okay, I'm going to go across as we do this. Valence electrons are the same for each case. Every oxygen is 6 valence electrons. Every carbon started with 4. Don't know why I skipped that one. And the nitrogens all have 5. So 6, 4, 5 all the way across. Okay. When we're counting non-bondings, we are counting the dots. Okay. So how many dots are on the O? There's 4. How many are on the carbon? There's none. On this nitrogen, there's 4. On this oxygen, there's only 2. 0 here. This nitrogen has 6. This oxygen has 6. This carbon has none. And this nitrogen has 2. Okay. When we're counting the lines, okay, so this is lines, remember, and the non-bonding electrons is dots. Okay, just so we have it there. Blah, blah, blah. Right. So we're counting the lines. You're counting all the lines that go to that atom. So for this oxygen, we have 2 lines. For this nitrogen, we have 2 lines. And for the carbon in the center, we have 4. Right. All the carbons, right, should have 4. So that makes sense. This oxygen has 3, so we'll subtract 3. This nitrogen has 1. This oxygen has 1. And this nitrogen has 3. Okay. Now, if we want the formal charge, we're going to add up all these numbers, which is really, we're just going to subtract all these from the valence electron. So 6 minus 4 minus 2 is 0. 4 minus 4 is 0. 5 minus 4 minus 2 is negative 1. 6 minus 2 minus 3 is plus 1. 4 minus 4 is still 0. 5 minus 6 minus 1 is minus 2. Then over here, 6 minus 1 is negative 1. 4 minus 4 is 0. 5 minus 2 minus 3 is plus 1. No, that's 0. I'm an idiot. Don't trust my math. Okay, so when we're looking at this, now we got to figure out which one is going to be the best. Okay, so we're going to have to rule out 2 of these Lewis structures. The first one we can rule out is this guy in the middle. This one is not the best. And the reason this is not the best is here. We have too much formal charge. Right? And if you think about it, this is a little bit weird. All of these add up to minus 1, which is what they should because our formula has a negative 1. Okay. Excuse me. But here we have a plus 2, a plus 1, and a minus 2. So 2 atoms have formal charge. This is not a good thing. And we have a minus 2. Okay. This is what we call a high magnitude of charge, right? Because regardless of being plus or minus, there's still a 3 charge here where the other ones only have 1. Okay. The other 2 have one, have the same idea, right? They're both 0, 0, minus 1. Okay, that's as good as you're going to get in the low charge with a -1. Okay, so the tiebreaker here is we have to decide what is more electronegative, because we want the negative charge, oops, negative on the more electronegative atom. Okay, so we got to ask ourselves, is oxygen more electronegative or is nitrogen more electronegative? Okay, if we remember our trend, oxygen is more electronegative, so this one is also not the best. Okay, this one where the oxygen has the minus charge is the best Lewis structure. Okay, you can theoretically do this with any Lewis structure you want. I will say that you don't always have to do it for everything. Okay, if you're looking for something and it's specifically asking us for the best Lewis structure, then we're going to have to use formal charge to figure it out. If we're just looking for a valid Lewis structure, it doesn't say anything about best, then you can do just anything that obeys our guidelines for Lewis structures. Okay, right? So make sure everybody has an octet that needs an octet. If it has more than 8 on the octet, it needs to be period 3 and higher, and all that stuff that we've already talked about. Okay. Let's look at one more example. Let's draw what we think the best Lewis structure for a sulfate is going to be. Okay. This is going to be a little less intuitive, so we're going to work through this. Okay. All of these are in group 6, so 6 times 5 is 30. Plus 2 more for the negative charge is 32 electrons. So what we're going to have is a sulfur with 4 things. Each one of those is an oxygen, and we have all these electrons left over. And by the time we get 6 electrons, 3 pairs on every oxygen, we have used all 32 electrons. And we're going to look at this and we're going to say, okay, we don't have electrons left over. Our central atom has an octet. We've used all of our electrons. There's brackets and charge on this thing, so this should be good. Okay. This is a valid Lewis structure. Okay, but it's not the best. Okay, and it's not the best because of the formal charge. If we look in here and start calculating formal charge for us, okay, we have 2 kinds of atoms. We have a sulfur that has 4 bonds, okay, and we have oxygen that has 1 bond and 3 lone pairs, okay. We have 4 of these, but they all look the same, okay. All right, so we're going to make our table. Here we go, valence, non-bonding, half of the bonding will give us formal charge. Okay, so we're going to prove that we have too much formal charge in here. What am I looking for? I'll just do blue again. That's fine. Okay, each of these started with 6. Sulfur has no dots on it, and it has 4 lines, so this is a +2 situation. Each oxygen has 6 valence electrons to start and has 6 non-bonding electrons and 1 line. So each oxygen is -1. So if we want to add this up, 4 times -1 is -8. Well, that's not true. 4 times 1 is 4. Oh my gosh, I could call it quits today. So yeah, so this has a charge of -2 total, but this is way too much formal charge. Okay. So what we're going to be able to do though is, because now is sulfur in period 3 or higher? Yes. So we can make sulfur take more electrons away from the oxygen to lower the formal charge. Okay, let me see what we're talking about here. Oh, that's not what I'm talking about. All right. So when we're fixing this and we want to get the formal charge to go down, okay, we have to put, right, this is a positive and this is a negative. So we got to take some of the negatives and put them on sulfur. What this means is we can share, I'm going to highlight in red here what I'm changing, right? We're going to take away a lone pair from an oxygen and share with a sulfur. And if we do this twice, okay, then that'll give us, use your words, dummy. That'll give us something that has the lowest possible formal charge, okay? We can prove it to ourselves. Let me get this picture out of here, okay? Right, now, let's see, our sulfur is gonna change. These kind of oxygens are gonna stay the same, okay? We don't have 4 of them, we have 2 of them. The other 2 oxygens look like this, okay? Our sulfur and our oxygen each started with 6, okay? Sulfur now has double bonds. So this has still 0 here, but it has 6 lines to it. So this makes 0. And then this one has 6 non-bonding and shoot. I should really do this video over, but you're getting full stupid today. So there you go. Right, 6 minus 4 minus 2 is 0. All right, you see what we did? The sulfur charge went up, no, went down to be more closer to 0. The oxygen charge went up to get to be 0. Okay, and now we have 2 times minus 1. This is still minus 2, which is what our total charge should be, but the formal charge has come down. So really the best Lewis structure for sulfate has 2 doubles and 2 singles. They don't have to be in the orientation that I'm drawing them. They just have to be 2 doubles and 2 singles. And I'm sorry if this got stupid. Okay, it's late. Okay. Eh. There we go. And brackets and charge. Okay. All right. One more thing we want to do is tackle something like this. Okay. We have a Why is this happening? Okay. We're going to tackle something like this. We have a chlorate ion and we want to add electrons to complete the best Lewis structure. Here's our keyword. Best Lewis structure again. Think about formal charge. Okay. So chlorine has 7. We have 3 oxygens, each with 6, and we have a negative charge, so we're going to add 1 more to this. So this is 6 times 3 is 18, plus another 8 is 26 electrons. Okay. Let's follow our rules and put them on there. We've already got 3 pairs in the middle, so we can subtract 6 and have 20. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That used 18. And so we have 2 left over. Those 2 go on the chlorine in the center. Okay. We need brackets and a charge. Okay. This follows all our rules. We have 8 electrons on everybody. We've used all our electrons. Nothing's left over. Okay. But if we look at this, and if we remember what we did over here, right, our oxygen with a double bond and 2 lone pairs is 0. An oxygen with a line and 6 dots is -1. So every one of these chlorine oxygens is -1. Okay. For the chlorine, valence electrons are 7. Non-bonding electrons are 2. And half of the bonding is 3. So 7 minus 2 minus 3 is a +2. So we have -3 + 2. It adds up to -1, but we need the formal charge to go down. This is way too much formal charge. So what we can do, and erase this to get out of the way, is we can make multiple bonds. Okay. Hint, since we have -1 here, we probably only want 1 single bonded oxygen in our picture. Okay. For the sake of this, remember each of these oxygens with the 2 bonds is going to be 0. Okay. We haven't added extra electrons in here. We've just rearranged the ones we have. Okay. Now, these two oxygens on the bottom are 0. Let me. What? Okay. This oxygen is 0. This oxygen is 0. This oxygen is -1. So far, so good. Our purple chlorine, then, that we just, the chlorine now that we've fixed it, I guess I should say, still had 7 valence electrons, still has 2 non-bonding electrons, but now it has 5 lines. And 7 minus 2 minus 5 is 0. So all zeros and a -1, that's as good as we're going to get. I'm sorry for being extra error-y on this one, but hopefully that makes sense. If you have questions or need anything, let me know. Feel free to whatever. Okay. Have a good one, and I'll catch you later.